Okay, so next we're going to talk about speed and velocity graphs. So when we're looking at a speed and velocity graph, the first thing we want to do is be able to tell during an interval or some section of the graph what's actually happening, right? So we want to identify places where, well, what are the possibilities, right? We could have either a constant speed, we could be not moving, right? We could have no speed. We could be getting faster, or we could be getting slower. So these are really our four possibilities. Now you could say that these are sort of the same thing, right? But we're just going to say C. We're going to label things as C for constant speed versus V equals 0 for not moving, just to differentiate the two, right? If you're not moving, then your speed is constant, but at 0, it's a special case. So if we look here during interval AB, the speed is just not changing, but we do have speed. So this would be a constant speed. During interval BC, we're going from a speed of 2 to a speed of 0. That means we're getting slower, right? So when we're approaching the x-axis on a speed graph, that means we're getting slower. During interval CD, we would have no speed, right? We're at 0, and we're staying on 0 for that interval. During interval DE, well, if our speed is 0, really the only thing we can be doing is either staying at 0 or speeding up, right? So our speed is getting larger. We're going away from 0. And then during interval EF, we're slowing down again. Okay, so in terms of acceleration, this tells us a lot about our acceleration, right? If we have a constant speed or we're not moving, right, and we're staying not moving, then we have an acceleration of 0. Now, this doesn't necessarily, like when you at 0, it doesn't mean your acceleration is necessarily 0 when your speed is 0, right? When you are maintaining a constant speed of 0, then your acceleration would be 0. If you're at a constant speed and you're maintaining that constant speed, your acceleration is definitely 0. And in this case, for this interval, CD, our acceleration is 0 during that interval, right? And we'll look at an example of when the acceleration doesn't necessarily have to be 0. But the acceleration is 0 for this interval and 0 for this interval, right? Now, if we're getting faster, right, generally speaking, we don't know on a speed graph what direction we're going in, right? So we would say that if we're getting faster, our acceleration may as well be positive. And if we're getting slower, our acceleration may as well be negative. Now, this whole graph could be depicting motion to the west. We don't know, right? It's not part of speed to tell us the direction. But since we're talking about one-dimensional motion, we're assuming that this thing is always going along a one-dimensional axis, right? It's either going east or west or north or south only. Now, in the real world, in the real sense, this could depict motion in any direction. This object could be going to the west at a constant 2 meters per second, slow down and stop, hang out there, and then start going north, right? Not important, right? Because any calculations we do with this would still be exactly the same. Because if we're talking about speed and we don't know anything about direction, then the only thing we can calculate is distance and not position, okay? So to calculate accelerations, all you have to do is look at the formula for how acceleration is calculated. Acceleration is a change in velocity with respect to time. So if you look at interval AB, you could take the initial and final velocities and subtract them. 2 meters per second minus 2 meters per second over 2 seconds. Well, that's 0 over 2 or 0. So, and we knew that, right? We knew the acceleration was 0. It's not surprising. If we look at interval BC, That would be 0 as our final velocity minus our initial velocity of 2 divided by 1 second, which is minus 2 meter per second squared. Looking at interval CD, the acceleration 0. If we go from D to E, it's going to be positive 6 meter per second squared. And if we look at interval EF, we've got a change of minus 6 meters per second over a time of 1, 2, 3, 4, 5, 6 seconds, which would be minus 1 meter per second squared. So the greatest magnitude acceleration here is during interval DE. And this should make a lot of sense because it's got the greatest slope. Okay, so what else can we do with a speed graph? Well, there's actually one more really important thing that we can do with a speed versus time graph. If you look at this interval here, and you calculate the area of this figure, what you'll note is that you would be calculating the area of a square or a rectangle. So 2 meters per second, if you multiply this by 2 seconds, the seconds cancel and you get 4 meters. So this is a nice little trick. You can actually calculate distances based on the areas here. And notice that this graph is always above the x-axis, so you're always going to be multiplying positive speeds by positive distances times, so you'll always get positive distances. You cannot calculate displacements here. There's no way of knowing what the final position of this object is. You can only know how far it went, right? So if we want to tally up the total distance traveled by this thing, we'd have 4. This is a triangle, so we would do base times height over 2. So 2 meters per second times 1 second over 2, which is 2 meters. Oh, sorry, 1 meter. 1 meter. So now we're up to 5 meters. We traveled 0 there. Our travel here is 6 times 1, which is 6 over 2, or 3 meters. And then the distance traveled for this figure here would be 6 by 6, 36. Half of that, 18. So we've got a total of 5 plus 8, and 18 is 26 meters of total distance traveled. Okay, so let's look at a velocity graph. So on our velocity graph, let's label these intervals A, B, C, D, E, F, and G. And you'll notice right away the big difference is the velocity graph has a negative axis, right? So we can do the same exact things that we did before. We can talk about when it's not moving, when it's moving at a constant velocity, when it's speeding up, when it's slowing down, but those things are indicated a little differently on a velocity graph in some cases. So for interval AB, we know that we're going at a constant velocity. And that's also true for interval DE, right? Constant velocities. Now, what about interval BC, right? Well, on the speed graph, when we had a positive slope, that meant we were speeding up. However, on a velocity graph, we're really interested in whether or not we're getting closer to 0 or not, right? We have a negative velocity, but we have a positive slope, which indicates a positive acceleration. So what does that tell us? Well, we should be well aware of this by now, that a negative velocity and a positive acceleration means that we're slowing down. Now, when we get to 0, does that mean, all that means is that we've stopped, right? We didn't stop accelerating. We're still accelerating, right? So this object starts out here at some point of origin. It moves at a constant velocity west for a while, and then it slows down and stops, right, when it reaches point C. Then what happens? Well, now it starts to speed up in the positive direction. How do we know it's speeding up? Well, it's going away from the x-axis. We have a positive velocity and a positive acceleration, which indicates that our speed is getting larger, right? So then we go back towards the origin for a while, and then speeding up, and then we move at a constant speed towards the origin. Then it moves, then it slows down, stops again, right? The velocity is 0 right here, but again, we immediately start accelerating again. So the acceleration is not 0 there, right? It just switches instantaneously from one acceleration to another. So here we're slowing down, and then here we speed up. Now, does this make sense? Well, we have a positive velocity, and we have a negative slope, which means we have a negative acceleration. Here we have a positive velocity and a positive acceleration, so we speed up. All right, we can calculate our rates of acceleration just like before. If you want to calculate the rate of acceleration for interval BC, that would be, so we go from -4 to 0, so 0 minus -4 meters per second over 1 second, or +4 meter per second squared, which is exactly what we said. We should have a positive acceleration. Note that the acceleration for interval BC is exactly the same as the acceleration for interval CD. So this object was going in some direction, slowed down, stopped, and went in the other direction without changing its acceleration at all. Okay, note that this is the steepest slope, so this is also going to be the greatest acceleration on our graph. Our acceleration over here for interval EF would be 4 over 2, or 0 minus 4 over 2, which would be -2 meter per second squared. And our acceleration over there would be 2 divided by 2, +2 divided by +2, or 1 meter per second squared, positive. All right, and our acceleration for this interval is obviously 0, and our acceleration for this interval is also 0. Okay, so the other thing that you can do with this velocity graph, similar to the speed graph, is you can calculate distances, but not only distances, you can also calculate changes in position, right? So let's say we start at some origin, right? And this is point A. Point B is, well, where is point B relative to point A? If we're calling point A our origin, B is going to be to the left or to the west of point A. Well, how far? We can calculate the area of this. -4 by 2, -8 meters is our area there. So B is 8 meters to the left of A. Then point C, again, we're still traveling to the west here, right? So we have 8 meters of travel here, -8 meters. This would be 4 by 1 divided by 2, or -2 meters, right? So C is 2 meters to the left of point B. Now, what happens here? The object starts moving in the positive direction. And notice this is going to be the same area as that. So point D is in exactly the same point as B. And then this area is exactly the same as that area. So this point, let's call it point X, is right where A is. So at a time of 6 seconds, this thing will pass back through the origin, right? At 6 seconds, it's going to be here. So at 2 seconds, it's here. At 3 seconds, it's here. At 4 seconds, it's here. And then at 6 seconds, it's there. And then we continue past that point, right? And we can calculate this area would be 4 by, so this is +8, +2, and this area would be +4. This area is going to be 4 by 2, 8 divided by 2, +4. And then this would be 2 by 2, 4 divided by Yeah, 2 by 2, 4 divided by 2 is 2 meters. Okay, so the final displacement of this object, you can cancel out these areas and we end up with a final displacement of plus 10 meters, right? 4 plus 4 plus 2 plus 10 meters. So this thing ends up plus 10 meters to the right of its point of origin. What's the distance traveled though? Well, to get the distance travel, you have to add everything up, right? So we have 10, 10, that's 20, and then 30. So the distance traveled would be 30 meters. But the final position, positive 10 meters. And there you have it, speed and velocity graphs.